Oftentimes, we not only want to find the maximum matching, but also find some good matching. Of course, there are many different situations and different ways to define what matchings are good. And one of the natural concepts is the following stable matching. So let's consider the following situation. Let's say you have n heterosexual men and n heterosexual women. And then they somehow have to form some matching between them. So all of them have to be, let's say, married. So they have to marry, and every man has to marry some woman, and every woman have to marry some man. Of course, this setup is totally outdated concept. I mean, some people does not have to get married, and then some people are not heterosexual. But for the simplicity of explanation, let's consider, this situation. We ought to find the marriage, so we have to match them. But we want this marriage to be stable. So when marriages are, stable, so in order to define when marriages are stable, let's say you have A and B, A prime and B prime. So this marriage and this marriage, in order that to be stable, what should be true? If this guy prefers B over B prime, then he doesn't want to stay in this marriage and then go to match with B. But however, if B does not prefer A prime over A, then B has no motivation to break this marriage and go to here, right? So when it's unstable, if A prime prefers B over B prime, then B also prefers A prime over A, then they have a motivation to actually break their current marriage and then form a new one. So in that case, we want to say this is unstable. So we say that assumption is that every guy here, every people here and people here have a preference orders. They have some ordering on the counterpart so that they prefer the highest on the order, and then they doesn't want the lower preference. So given, say, this preference order, or say it's vertex of K and N. So you have N vertex, you add all the possible edges, because anyone can be matched. It's just a matter of whether you prefer such a matching or not. One, it's neighbors. So each vertex has neighbors, and then it has a preference orders on its neighbors. And purple matching is stable if there is no unmatched state. So these two, something like these two. No unmatched adjacent pair or vertices such that each prefers the other to its current partner. And we call such pair is called unstable. And then if there are no unstable pair, then it is stable. And the natural question is that if we have such a preference orders on each vertex, can you find the stable matching? There is this Dale and Shapley's proposal algorithm. And let X and Y be the bipartition. Of A and M. And what we do is each vertex in X, they propose to the highest Y on its preference list, preference order. Who that's not rejected. Rejected the order. So each one of them, if propose to here, and then here, and here, and here, here. And once if it's Y receive the only one proposal for everyone, then we stop and use the resulting matching. Otherwise, what do we do? Every Y which receive more than one proposal, rejects all except the one with one who is highest on its preference list. And we repeat this. So meaning that this guy got 3 proposals, and then out of them say this one is the highest on its preference list. Then what? Then these 2 people are rejected. And in the next time, what? Then this guy is not rejected by the first one, so it's still go to the this one, go to the same person. Then this go to the same person, and then this was not rejected. But these 2 guys were rejected. These 2 were rejected. So if this person was highest on their preference orders, but they got rejected, they go to the second person. And maybe the second person on their preference list are on here and here. Then these 2 people have more than one proposal. So out of them, they choose. Maybe this guy now accept this one, then this guy rejected, and then say this guy rejected. And in the previous one, this was not rejected. then this was not rejected, and this was not rejected, and the other two got rejected on their, this one was rejected on their first one. So you go to the second highest person on your list, and then this guy gets rejected by him and him. So you go to your third on the list, and then that happened to be different on the other remaining. And this is what the proposal looks like at the next turn. And then this is the final resulting matching. And in this algorithm, we can check that this proposal algorithm produces a stable matching. First, we have to check that this algorithm actually terminates. It produces the matching. And what? In this iteration, the total length, so each one of them has its preference order on n people. So it has list of n, and then each time it gets rejected, you delete one. You delete one, and then your list gets one shorter, your list gets one shorter. The total length of lists for potential mates for the vertices in X decrease. It decreases by at least one. And this decrement can happen most n square times. So it terminates with some matching. Okay, so this shows that this actually terminates with some matching. And we have to check that the final matching is actually a stable matching. So during the algorithm, what happened? Excess proposals are effectively decreasing. So you go to your first choice, and then you get rejected. You then move on to second choice, third choice, and so on. These are successively non-increasing in its in their preference list. And what about Y? Y is matching. Initially, Y gets some proposal, and then you choose one out of the best. And then in next time, you get another, proposal, but the winner part, the winner before, the one you didn't reject before, are still proposing to you. So you keep it, and then you don't change unless there are better match. If some other person proposes and then you like it better, then you change. So Y's match are actually increased. Successfully non-decreasing in its list. So, but if assuming the result is not stable, then what happens? Then it has an unstable matched pair x, y, where x matched to say y prime and y matched to x prime. So x is matched with y prime and then y is matched with x prime. And then this is unstable pair. Assume that. Then what do you know? As if y is matched to x prime, and what? X is higher on the preference is to y. So this being unstable means that y prefers x over x prime. Sorry, somehow the sharing stopped. Okay. So that means that the x level proposed to y. And obviously, if x proposed to y, then y will switch to x. Because x prime is no longer, x prime is rejected, and then it no longer proposed to y. So y would have never matched with x prime. But what do you know? However, x would not have proposed to y prime without earlier proposing to y. Because x prefers y over y prime. So x would have proposed to y before y proposing to y prime. But this is a contradiction, right? And if x would have proposed to y, then they have to be matched, teaching x prime. So this contradiction confirms the stability of the resulting matching. This proves that the Diffie-Chevrolet proposal algorithm actually produces a stable match. Okay. What one can also check is that there could be multiple choices of stable matching. Stable matching may not be unique. And out of all those choices, there are better choices for the certain. So if you have two stable matching, obviously, I mean, this guy is matched with him, this guy in one matching, and then this guy is matched with another one in another matching. And for this guy's perspective, one matching is better than the other because this has some preference out of these two. If this prefers the upper one, then the matching which give you a match with the upper one is better for this person. So for each vertex, there are one stable matching, which is also best out of all choices. Actually, there are out of all stable matching, there are better choices. There are choices which are best for all the vertices in X altogether. So out of all stable matching, this particular stable matching is best choice for every single one of them. And on the other hand, they are worst for all vertices in Y. This choice is. And you can actually prove that one is what you get from this proposal algorithm. If you do proposal algorithm, then it gives you one stable matching. Out of several possible choices of stable matching, it gives you one. And that one is best choice for all the members of X. And then worst choice of all the members of Y. So the one which proposed, the one who tried to approach, ends up with a better situation than the ones which are like getting proposed. Anyway, we will not prove them, so I just mention that as a knowledge. Okay, so this will conclude the discussion about matching, and the next time we will talk about connectivity. And before we learned about the definition of connected, and then we studied the minimally connected graph, which are the trees. And then we will learn about, slightly more connected graph, and then their structures and properties in the next lecture. Thank you very much. See you in next time.